Thanks, everybody. Welcome. We will get started shortly. Okay, I think we should get started. Welcome to the March 2025 edition of Green Infrastructure, Climate, and Cities. My name is Franco Montalto, and I'm the director of the Sustainable Water Resource Engineering Lab at Drexel and co-investigator for CC-RUN, the Consortium for Climate Risks in the Urban Northeast. CC-RUN's been funded by NOAA since 2010, and we've been doing this webinar series since 2014. Each of our seminars is recorded and archived on the CC-RUN website for you to review at any time. So please feel free to come back to this particular webinar on the CC-RUN website. We'll post it within a couple of days, or to just check out any of the archived talks that we've had going back to 2014. And as you know, if you're professional engineers, we give continuing education credits as long as you've registered for this session. Next slide, please. So today I'm excited to introduce the topic Innovations in Storm Surge Protection and Coastal Resilience, and our two speakers, Giovanni Cecconi and Coraggio Maglio. Giovanni and I have worked together for a variety of years. I bring students to Venice and he generously shows us all around. And Giovanni and Coraggio have worked together in a bunch of different capacities. So it's really exciting to have them both here to share their experiences with us today. So what I'll do is introduce Giovanni first. He'll give his talk, and we'll have just a few minutes for specific questions about Giovanni's talk. And then Coraggio will give his talk, and we'll have some questions for him and general discussion at the end. So with that, let me give introduction to Giovanni Cecconi. So with 35 years of experience in a variety of leadership roles within the MOSE project in Venice, Italy, Giovanni's become an expert in storm surge barrier design and environmental adaptation and mitigation strategies. His expertise is vast and broad and extends to the transport processes of sand and soft sediments in sort of complex hydromorphological and socio-ecological systems, as well as in the design of a variety of different nature-based solutions in coastal environments. And during this past trip, when I went to Venice, Giovanni showed us a brand new island that had formed in the Venice Lagoon. As a consultant, manager, and scholar, Giovanni focuses on green and blue solutions for coastal cities facing a variety of climate change challenges. And so he's keen to foster a variety of sort of discovery-driven partnerships for the adaptive co-management of coastal ecosystems. So I'll also introduce Coraggio Maglio, but we'll begin with Giovanni's presentation. So with 2 decades of experience, Coraggio Maglio has worked on environmental restoration, coastal engineering, and water resources. He has 14 years of experience at the U.S. Army Corps of Engineers, working on design projects, managing very diverse teams, and he's done studies all over the globe. His primary skills lend well to the program management of large-scale water resources projects. And he's known for being a leader-doer. And I was just in an event down in Houston these past couple of days, and that was certainly, when I mentioned that Coraggio was going to be our speaker, that was what I was told. You got a leader-doer coming to your talk. And he's known for bringing out the best of individuals on multidisciplinary project teams. So thanks to both of you for joining us today. And this is an important session on barriers. These are sort of becoming more and more surge protection. Coastal barriers are becoming part of sort of dialogue in lots of different coastal environments. So I think this is a really apropos topic. And with that, I'm going to hand it over to Giovanni. Giovanni, if you don't mind turning on your audio, your video, and sharing your screen, and we'll get going.
Okay, hello.
While Giovanni's pulling up his slides, I'll just mention, please use the Q&A for questions, and reserve the chat will just be for logistical questions. But put Q&A in the chat, and I will orchestrate a discussion at the end. So thanks, Giovanni. We can see your screen. You're good to go.
Okay, thank you for this invitation. It's a pleasure for me to present you the Venice experience, my 40-year now experience with the Venice Lagoon adaptation and coastal protection. Venice is a complex dynamical system and went through co-evolution during the last 2000 years. Here in this picture, you can see the complexity: an historical city, a wetland, an habitat, theater, opera, mass tourism, fishing harbor, and the beauty of the city and the lagoon altogether. Also an aging city, so lack of population. Essentially, the Venetians started living and learning from nature and water since the very beginning, because it was a very big challenge to live in the tidal environment without food from agriculture, without water above all. And so what they did was to reclaim the soil out of the marshes in the beginning. Here you can see the fish farming. That was one of the main activities related to the production of fish, but in an extensive way to take advantage of a natural environment. But the first business was related to salt farming, and because the salt was very strategically important to survive the period of challenges you had with others, because if you are well fitted, you can do a confrontation, otherwise you cannot. And the Venetian understood pretty well, and so what they did was to get enough food to strive and be healthy during their civilization since the very beginning. All the other goods were imported, so they had to develop the trading activities to survive, because they had to import all the other goods. And when they started fishing, they understood also how to build ships, and that's why they became the most and long-lasting, the most important and long-lasting merchant republic for 700 years and more. This is how in 1700 the competition and co-evolution among nature and the society was represented. It's kind of an embrace, but also a fighting, and it's very difficult to distinguish if the two figures that represent the land on the left and the water on the right are embracing or fighting, because there is this attention. And now there is this new word that is co-petition, meaning this attitude. Indeed, in the beginning, the settlers had to move according to the mean sea level. From Neolithic age, you can see the remain of these people living in and out. But then in 1700, they started directing the river out and protecting the city with the settling above the high waters. And because of that measure, now the lagoon is suffering from a lack of sediment. Also, they protected the barrier island, rediscovering the Roman pozzolanic cement, And this is a good example of coevolution. In 1875, there was a big shoal in one of the inlet of Chioggia, and the fisherman that went fishing at sea, at the end found their uh, bad luck in front of the entrance, because during the storm you have shoals that are unpredictable. And so after 50 years, they have been able to install inlet breakwaters, and nature took over and exploited this situation, because in the pocket on the right here, a new protected area developed with that is a bird sanctuary now. Even though in the beginning the environmental impact in terms of landscape was huge, at the end, this flow of sand accreted in this area and produced a dune field with the beach that is growing at a rate of 5 meters per year now. In the lagoon, instead, the sea level rise transformed the shoals of 1955 into this deeper tidal flat. But in certain spots, the vegetation took over. And here you can see more clearly that the starting are related with the formation of microbial mat. So the soil is paved by this cyanobacteria that can make the soil very firm, and then the vegetation can come because of the fertility and stability of the soil. So essentially, small local interaction are driving the formation of the landscape. Now there has been an acceleration in sea level rise of twice, as you can see from this drawing. This is the average, the red one below, and this is the present from 1990 till now. And it seems that it's even increasing recently, because even though it's not regular, this rate is increased, and there are jumps, period of wet and dry, but the dry spells are shorter and not so intense as it was in the 70s. This is a consequence of increasing the energy that the lagoon can receive from the wind. And the ratio, it goes with the third power, because the waves are limited by the water depth. And if you double the depth, the energy of the wave and the size of the stone goes with the third power. So this means that the environment is not stable anymore if you double the water depth, as it was the case. And if we add another 40 centimeter, the energy, the rate of the energy in comparison with 1800, in which the lagoon was sinking, was in a under the danger of siltation, essentially, is 16 times more.
Excuse me, Giovanni, I'm sorry to interrupt you. Someone mentioned that there's a box at the bottom of the screen that is covering up.
Oh, sorry.
Can you?
Okay, it's clear now. Yeah.
Yeah,
I
that's
think.
it. Thank you.
Okay.
There was a note coming. So the first sign of this effect of sea level rise is the clogging of the small creek. From 1930 to 1970, the first index of siltation is the clogging of the smaller channel, and then the deepening of the tidal flat. And so the lagoon is becoming a bay now because of this increasing wave energy and lack of sediment. But the main driver was the relative sea level rise. So we can say that both the city and the lagoon experimented the impact of a climate change during the 1930-1970 relative sea level rise, without considering the present acceleration. So the tidal flat disappeared, while the salt marsh in this picture were not so badly impacted. Because if you see here, whatever is in the 0 minus 60, that is inside the minus minimal tide and the average, went from 160 square kilometer to just 60 kilometer, while we had a reduction in wet salt marshes of just 20%, from 60 to 40 square kilometer. So this means that the process is self-accelerated, because the deeper, the higher are the waves, and the more is the energy, and the wider is the fetch. So everything is with a positive feedback that is amplifying the erosion. That is also transferred to the edges of the deeper areas. And this is the effect on the depth of the tidal flat. So everything, we have data only into this period, 1970 and 1900. Also 1930 here, there is another point. So something happened during the industrial, when the destruction of water started and the subsidence started. The other impacts, such as the opening of a new channel or mechanical fishing, are playing a minor role, because the trend is maintained. There is not any acceleration. There is only a limitation, because when the bottom reach around 2 meters, theoretically, the erosion will stop. So this is the impact. And of course, this has also environmental consequences and lack of loss of biodiversity. This is the loss of sediment. Around 600,000 cubic meters of sediment are lost to the sea, but the majority of sediment goes into the canal. So the canal are not able to maintain their depth. So maintaining the lagoon canal is becoming more and more expensive exercise, especially because the sediment are polluted, and there is a very complex legislation that allow the dredging. So while nature, the wetland are taking over the sea level rise, in the city you cannot adapt that much, because at a certain point you are not able to walk through the ground floor. So the solution is to demolish and build on top, as some archaeologists suggested, the business as usual. Of course, we wanted to make a barrier, and so we're very much against this philosophy. And so at the end, was well accepted to make the storm surge barrier. But let's spend some time more into this 7 natural engineer I introduced to you. So the reed in the mouth of the river, the allophytic vegetation, the Ammophila littoralis in the dune system, the macrozoobenthos, the angiosperm, the eelgrass, and the microbial mat. I think the number 6 is the more important, because it's the starting point of stabilization of the shoal. So this is the mechanism that allow the build-up of new island. And of course, the oyster and the mussel reef. These 7 engineers at the end are fundamental for the food chain and the biodiversity of the Venice lagoon. So the solution for Venice, adaptive solution, is to enhance the salt marshes and shoals, reusing the dredged sediment that we have to dredge because of the imbalance I presented, to nourish also the littoral, mining sand at sea, to increase the local protection because there is a need of restoring, of maintaining the city and the infrastructure, but we can do that till a certain limit. We just did a rising of the edges of 20 centimeters. We can try to do more in case of an acceleration of sea level rise. But the very solution is to control, to keep the sea out of the lagoon when there are major flooding. So this is a complex system of solution, and most of them have been done. Littoral protection, the flap gate, the local protection, and the morphological restoration. Just I will leave this picture for the questions because these are business as usual solutions. So this was the situation, overtopping, and you see wave overtopping here during the 1st of November 1966. And the solution was beach nourishment. This is a special beach nourishment because we spend 50% of the money for the sand and 50% for the armoring with this submerged breakwater and groins in order to maintain the volume. And now, after 30 years, the volume is still there. It's incredible. We lost a very little amount. Local protection of the historical island because this monastery were settled by the pilgrim and the monks that provided the logistic for the Holy Land. Industrial area, abandoned dump site, and also bioremediation of non-point pollutions. The illegal dump site and the local protection. There are many, many kilometers before and after. And in Chioggia, a small fishing village in the southern part of the lagoon, there we made a local protection combined with the gate into this area in which we was not possible to rise the edges of these are the small gate in Chioggia, very effective. Chioggia is also a special place because it usually get 20 centimeter more of water due to the northern wind. And so if without this system, we had to increase the number of closure by 2 or 3 times just for the sake of protecting only Chioggia. Now the demand for protection in Venice and Chioggia is homogeneous because Chioggia is protected locally to a higher elevation. This is San Marco Square with a special glass and steel screen that has been completed, and now the whole square will be protected in order to reduce the number of closure because this place is very shallow. It's only 80, 100 centimeter now, and we want to keep this local protection till 100 because now it's flooded more than 200 times per year. And the marble of San Marco Square have been ruined by this frequent flooding. That's why the barrier of steel and glass was installed. But it's not enough because also the economical activities in the square are impacted if we do not stop locally this very frequent flooding that are unsustainable in terms of interaction with the harbor activities, because anytime we close the barrier, we have to redirect the navigation through the navigation lock that was not completed yet. And so this was a great challenge among the city protection and the harbor activity, economical activities. The restoration of and construction of artificial salt marshes, the protection of the edges and the island. Okay, so you can see more than 95 sites have been protected with 16 million cubic meter of sediment. And we had a lot of salt marshes and mud floods. And this was the situation 5 years ago. Now all of them have been completed. This is an example, very similar. So just we make a confinement, very expensive confinement. The cost of the confinement is similar to the cost of dredging and transporting and pumping the mud and sand on top of this area. But there are environmental regulations. I've seen that in other places, instead of doing this, you just make with the local material a mound and you pump inside. So you can save 50% if you accept that turbidity. So my suggestion was to do the job in winter when the lagoon is very turbid, but the bureaucracy did not allow that. So what we did was at the end to go through the whole situation of spending 50% of the money and to do the confinement. That is made with different gabion stones or wood pole that don't last that much with hydraulic net on geotextiles. This technique, thin layer nourishment, I visited New Orleans and the local Corps of Engineers. So I spoke with the manufacturer of this equipment and I brought in Venice and it was very successful. It was 25 years ago. So now we have good data on the internet because with this you can remove the mud and pump locally. We just closed the small creek entering the wetland in order to induce a higher sedimentation of this jet spraying, or the opening of new channel or transplanting of vegetation. Also the sedimentation screen with John Day, we visited this last year in New Orleans, in Baton Rouge, is very effective. He imported from Netherlands. So you see this natural-based solution are traveling a lot. Netherlands, New Orleans, and back to Venice. Bowman was a student of John Day that helped John to develop the set table and also to model the accretion and the landscape model that was then applied by Bob Costanza to plan the management of the Mississippi Delta as a whole, as a landscape model, so-called. That kind of modeling now are continued with the better computational capacity. Also in the University of Baton Rouge, there are nice scientists that are able to predict the value of not screen sediment, but land bridges, they call. So to make stripes of shoals land in order to reduce the fetch and trap the sediment that the river discharge into the near coastal area, and the storm can bring back on coastline. If this coastline is equipped with pockets in which the sedimentation can be enhanced, the most large quantity of this sediment is trapped back to the delta. So we do not allow the delta to meander, but we make the absorb capacity of the delta higher. And a lady I met with Maglio last year, Polly, is just behind into this, and it's nice to share this international experience because we are doing the same, but in other environment and with other tools, but the mechanism, underlying mechanism is the same, to keep the sediment locally to accrete and help the microbe and vegetation to build up, to help in building up the volume of the soil. This is the different stages of fencing, pumping, in this case sand, and the stages. We have all the data about the monitoring, what happens after 2 or 3 years. And this was my monitoring. I was in charge in 2008, 17 years ago. So now the older is not 15 year, but is a 32-year-old, the first constructed marshes. So we have plenty of data, and Venice is becoming an international laboratory on building with nature solutions. And of course, you are invited if you come to visit, because now I am running a business of international visitors coming to see the barrier and the wetland, and I organize everything. And with the money I collect, I pay for the cost of the traveling and produce a benefit for the young student that can learn at the same time. Make a team for access to European funding or support international visitor, like the student from Philadelphia with Franco. When they come, I can provide 1 week or a few days of training at cost or less, because there are also local students that help me into that with the money we collect from the tourists. So this is a way of involving the tourist into the maintenance of the system. So it can be a form of sustainable tourism. Some picture I have to run. How many minutes, Franco?
You still have, it's only about 30 minutes. You have time.
Okay, so these are the biodiversity index. It's very interesting to see that the bird like this neoformation environment more than the natural one. They are attracted by the shoals, oyster catcher, for instance, but many others, the fish, the tern, little tern, they like the neoformation environment. So a biologist at a certain time said it's better that we destroy the vegetation and expose the bare soil, or we continue to make new salt marshes constructed, because this is what the bird like more. And there are many examples. For instance, this is the shoal, and that became an island thanks to the barrier. Because of the closing of the barrier, the overtopping of the wave was stopped. And this produced a growth of vegetation. And now this shoal, that was an ephemeral shoal that was destroyed during the winter, it's permanent. And these are the holiday makers that go into this new island with the beach. And of course, the bird cannot stay there when all these people is competing for the same little spot that is now 200 meters, but there are possibility, as you see here in this breaking wave area, that in few years it will become half a kilometer or more. And the vegetation is still there. I checked last week with my board that the no wave overtopping means stable vegetation on top of the shoals. So this is me in this picture, and also the new constructed wetland are providing amenities and sentimental landscape, because when organized my tour, the one that join my tour are mainly artists that find inspiration visiting this constructed wetland with me. I do not know if you see here, but this is something I did 30 years ago. It's the shape of you see this little shape. This is completely artificial, but people commented, oh, look at nature, what nature is. It seems it has been drawn by an engineer or an architect. This is the biggest, the greatest compliment I can receive. So they look at this as the top expression of a natural system. Instead, this is the expression, a land art of co-evolution, man and nature interacting. And this has an aesthetical and sentimental value for many, apart from carbon sink, fish habitat, biodiversity, and all the many ecosystem services, as they are called now. So, my activity of adaptive hospitality by regenerative explorations is a way of maintaining Venice as the oldest city of the future, so can provide a paradigm for solving the present problem of harmony between human and society. In this time, there is a need of harmony also among humans, but this is another story. And I wish that the love for nature can also help in making the people more responsible and friendly each other. So in Venice, you can find top-down institutional exchanges and bottom-up community exploration. I think this is important. You can enter to Venice and learn both way, top-down and bottom-up. And my mission is to connect these two attitudes, because now I am with an NGO. And of course, there is the last issue I want to face with you is what will happen if the sea continue to rise? Because this is the problem of the last flooding that was 187 centimeters above the datum. And what is happening here? I am not able to push. It's frozen. The screen is frozen. Okay. Let's go back here. Okay, this one. Can you see the screen?
You just have to get rid of that thing. Yeah, there we go.
Okay. So there was, so the flooding. Oh, because there was the broadcasting of 1966. So as you see, sea level started since 1950, and now there is this acceleration. The 6 times more frequent, the extreme flood higher than 148. So 6 times more extreme flooding. It's a huge number. So Venice is very sensitive to this. It continues to be, I do not know what is happening. Okay. Maybe you can follow also with this.
Yeah, you can scroll through it that way.
Yeah, yes, I think there is something in the full screen. In Venice, you can also get proxy data of sea level rise. Looking at the painting of Canaletto, they use the camera oscura, so a geometrical projection. The black line is the mean high tide, so you can spot that mean high tide and transfer to here. And from that, you can tell, and this is from where I got this result of acceleration. So 1990, 20, 25 centimeters per century. So 1880, 25 again, but then 50 centimeters per century, the last period. And the difficulty in adaptation, the solution, and the combination of the local protection and the closure of the lagoon in order to reduce the number of closure. The system is under operation, and it has been used for 50 times, but the number of closure will increase exponentially if the sea level will rise more than 40 centimeters. We will go from the expected 5 closure per year to the present 20-25 closure per year, reaching an incredible number of more than 200 times per year. So this means twice a day. Of course, we can reduce this number of closure closing only one inlet, because this frequency is driven by the astronomical tide that is very regular, and it's enough to close one of the inlet. But we have to think also to other solution. And in my speech, I would like to present, apart from rising another 20 centimeter, the poldering of the lagoon. And because there are many advantages, if we start thinking, as I did in the interview with the Wall Street Journal, you can find on the channel of the Wall Street Journal, the idea is to make a super levee and allow the water to be 1 meter below the present, as it was in 1700 in the painting of Canaletto. Some architect thought about this extreme situation, an atoll around Venice. Me and my professor prefer this very simple, more pragmatic extension of the barrier island. But the idea is the super levee that can be overtopped without consequences, as it is done in Tokyo, Japan. We also made a competition in Boston for total resilience approach, and we won the first prize with this solution of a super levee in Boston connecting the two sides of the city. It was a 2014 competition of Boston 2070 with 1 meter or more water. And the idea was also to produce electricity upstream and pump the water downstream for Venice, I mean, not for Boston. Boston was more a resort to the seaside, a garden inside, and a transportation network on top with a natural park. So in Venice, we used to swim in 1833 in the canal with the floating swimming pool. And the lady used to swim in this gondola with the cage. And in 1700, all the people started learning swimming in front of the houses. Also in 1950, you can see. So this solution with the age of the water that will be only 3 hours old, this means no pollution. So we can swim again in the Grand Canal. Also, my motto is let the marble shine again, because now the black line is above the marble line. And here you don't see anymore this white line of the edges of the Venice. And this can be very interesting, because if we do that solution, we can clean all the entrances of the city and the marble and the stairs, and get rid of that. Also, there is no need of engine boat oil with CO2 emission and pollutant of the air, because we can use the ring around Venice and use only rowing or electrical transport inside. The tourists can be relocated completely out of the town. Only the people that are using the city in a sustainable way can live in Venice. The visitor will, like in the Yellowstone Park, you are not allowed to enter the natural area if you don't have a purpose and you don't know what is happening in that park. So with the same regulation, we can have Venice shining again. Thank you. I would like to leave the most details to the question, or maybe if there is more time, I also can explain the details of the barrier and why it will be limited in case of a sea level rise. Essentially, the limit comes from the lack of low tide. If even the low tide is flooding Venice, because during the closure, the water is rising due to the seepage through the gate, due to the rain, due to the river, due to the setup, due to the wind, And so because of this, we need to close 40 centimeters below the safety level in order to allow a certain storage at low tide, maybe 6 hours in advance. But if we don't have that low tide, we don't have the storage, and so the barrier becomes useless, the mobile barrier. The barriers are very elegant because there were many constraints. They had to disappear when not in use, and so they were made to stay below the water all the time with a huge cost of maintenance that is in the order of 5 times a year. We have to remove the flap and restore. But after this initial period, we have verified that the duration of the floodgates are not compromised if we do the maintenance only once every 10 years. This is a positive, is a reducing of 50% of the cost of maintenance. We had to solve a lot of problems, for instance, the differential settlement of the soil, because this gate, the caissons, are sealed with the technique of the immersed tunnel. So there is, as I will show you later in these drawings, here, this is a 7-story building, 27 meters high, that is transported on this with this trolley, each of them able to keep 80 tons. And they move little by little, 1 centimeter per minute, to launch into the water, because here the inertia is huge if there is an acceleration. And this is the frame with the rubber and the steel plate that produce the sealing of the tunnels. Let's see if there is another view. Maybe this one. This tunnel. Okay, this one. Eccola. I have to put this, open it work. Better not to do that. So the tunnel are 2 because there is a degree of redundancy of 4 times. Even though a tunnel is flooded or go into fire, the system will continue to operate because you can shift to the nearby tunnel. And the risk of not rising a flap on demand is in the order 1 over 10,000. But because we have around 80 flap, it drops down to 1 over 100. The probability that at least there is one that is not able to rise. If we know that this will happen in advance, we can close at a lower level and use the reservoir of the lagoon to dump the high tide inside, even though it's not completely closed. Also, we can use the system in a way that is useful to flush the lagoon if we close during the summer and there can be lack of oxygen or the risk of anoxia inside the lagoon. Here is the degree of redundancy. You see the water can enter through 2 different pipelines, through 2 different hinges with 4 connectors. So it's enough 1 connector to inject the air that is needed to raise the gate. In the well, there are many flap gates. Our solution is this one because we were not entitled to put any intermediate piers. Indeed, in London, there are piers, and there has been 2 collisions, a dredger and a passenger ship hitted against the piers. So it was wise not to have any piers in our case. In Japan, they are thinking about to use the number 3 solution against the tsunami. I visited Japan 20 years ago, and they wanted to know everything about the flap gate, because then they adopted this number 3 gate in order to stop the tsunami, because this gate can be put in place by the push of the tsunami itself. So you need just a string to stop the motion of the flap. And this saved a lot of life, because they used the gate to close the door of facilities on the coastline. Most of the people, even though they received the alert, went down to the coast to close the door and keep the resort, the asset safe. And so they had no time to escape. Now they can escape. They have 20 minutes, and to reach an elevation of 30 meters above mean sea level, a safe elevation usually on top of the building or in the hill. And the facility will be self-protected by the flap gate. So this is an interesting exchange of solution adapted to another situation. Contamination, let's call, of solution. These are the many gates in the world, including the New Rotterdam, MOSE land barrier, and the New Orleans, the Lake Borge storm barrier, the rubber Ranspool, very economic, the cheapest. And of course, the barrier in London, this one, similar to the one, but is a Newport concept, and the London barrier with horizontal axis. This is not a storm surge barrier, it's a marina barrage. It's a member of the Ice Storm Committee, that is the committee of the manager or the willing to be manager of the barrier all over the world. And this is for freshwater, preservation of the storm water season on a coastal lake, in order to treat this water and produce drinkable water to stop subsidence. So it is indirectly a system that prevents the flooding of the city, because without this water, like in Jakarta, you continue to extract, you may continue, as it is the case in Jakarta, to extract the water and produce 20 centimeter relative sea level rise per year. And Jakarta, sooner or later, will be, the people of Jakarta will be relocated.
Giovanni, about
Okay.
3 minutes, if you got.
Okay, just a pictorial view. I relax. Sorry for covering so many aspects with my broken English, but it's important that you get an impression of my experience and you visit Venice, and so we can better share this knowledge. It's very important also the mechanical aspect of the connection, because this has to be removable and has to stay in place. The accuracy of installation was crucial, 1 centimeter accuracy with this concrete, and only 8 centimeter every 60 meter of differential settlement. This is the size of the caissons that were launched in Malamocco, but we also had to worry about the installation of the gate and how to make the gate to pump the air in to allow the water to exit was even more difficult than to pump the air. And this is rather complicated. The tensioning bar that keep the assemblage with 300 tons of pull. The jack-up, it's a maintenance barge that will enter in operation again this year after maintenance. And The other system to make the foundation was the dry dock below the water level. And then this was flooded and all the caissons were brought in place with tugboats. The jack up in operation. Here you can see how it works. It's important to, I have to put full screen, but here you have to deploy the leg in order to have an accuracy of millimeters in engaging with this frame engaging the gate. And you do not have to be out of waves and current to do that. This is an example of intense operation of the barrier in October 2023. As you can see, we had the continuous flooding. When it is wet, it's very, very wet usually. So because there is the persistent of the Mediterranean Sea and Adriatic, the water is piled up, the cyclones are coming one after the other, and so you have this non-linear effect in the frequency of flooding that comes all together. So a very intensive operation. Now we reached the magic number of 99 closure, and we are waiting to celebrate the 100 closure. The control room and there is the operational rule are very simple. It's based on classification, and then the barrier are closed, measuring the water level, not deciding anything, not on forecast, on measurements. The forecast is implemented only to decide at what level we will close. Depending on the duration and intensity of the storm, there is a class of closure. The earlier, the stronger, the earlier, essentially. And these are the barrier during recent storm. So, again, I want to call the small water community for adaptive hospitality. This is my solution for the mass tourism, to introduce a new form of tourism that is based on hospitality, to teach adaptation through experiential trip in the lagoon, not inside the building, but on a barge, visiting place with the booths and sharing knowledge, but also sentiment. I think this is important now. Thank you.
Thank you, Giovanni. That was fantastic. There was a whole bunch of good stuff there. We have a lot of questions. But I'm wondering, given the time, if maybe I can just ask you 2 or 3 quick questions and we can transfer over to Coraggio. And maybe you can answer these quickly because they're sort of factual questions. One was the sediment that was moved into some of those containment areas. Was it free of pollution, or did it need to be cleaned in any way?
No, we assumed the criteria of not that if you reuse the sediment in the same area, you can do that if they are not heavily contaminated. So there were a classification limit based on the content A, B, C, and A and B could be reused locally. If it was a sea level, even though this potential pollution are not biologically available, we had to bring to a dump site or to treat it. Now we have also a bunch of biological tests, but these tests are making things more complicated. Nobody's taking responsibility. And it's very, very strange that we care so much about the pollution of the water, and we don't care about the pollution of the motorboat that are diesel engine. And Venice is the most polluted spot in Upper Italy, in the Val Padana, because the pollution of this boat is not removed by the wind, because inside the city the pollution is trapped.
Yeah. So, and there's one other quick question I'll try to ask you. Is anyone talking about reconnecting the rivers that the Venetian Republic redirected back into the Delta? Is anyone sort of talking about that?
People, John Day, for instance, insisted very much into that, saying that if we bring the sediment back, this will help the system to be regenerated. According to me, no, because sea level rise caused kind of an Alzheimer of the channel. So the water doesn't go along the channel, but there is a lot of cross flow. Cross flow means to move the sediment from the tidal flood inside the channel, as you see from the rate of siltation of the channel. So we need to fence the channel and increase the longitudinal current in order to maintain the canal. But then we need to trap the sediment. So there are plenty of sediment that comes from the erosion of the tidal flood. It is important to keep this sediment, as it is done in the Mississippi Delta, in the shallows. It's not so important to increase the amount of sediment entering the system, because a huge amount of sediment is mobilized 15 days a year due to the windstorm.
Yeah. Okay, I think we have two more questions there, but I think we have to move on to Coraggio's presentation. But I don't know if you want to, while Coraggio is presenting, if you want to look in the Q&A and maybe you can type a response. Otherwise, we'll save those for the end. But thank you, Giovanni, for this presentation.
Thank you.
And I guess we'll shift over to Coraggio.
All right, I'm shifting over now.
Perfect. Thank you so much.
All right, you should be seeing full screen right now.
Yep, perfect.
All right, so I'm Coraggio Maglio. I worked in the Army Corps of Engineers for 14 years. I left the Army Corps about 2.5 years ago before everything got a little crazy. That being said, much of my second half of my Army Corps life was spent working on the coastal Texas study in the Houston, Galveston area of Texas. And so today my talk's going to be covering a holistic approach to coastal resiliency. I'll walk through a lot of the history of the area, the activities that have been done historically, as well as the activities that are ongoing, and I'll beat around the bush on some of the things coming down the pipe in the future. All right, so what are the problems that we face in the region I work in, which is basically the region around Galveston Bay? You have the city of Houston, which is the 4th largest metropolitan area in the country. You have the largest port in terms of tonnage in the country. It's a huge economic driver for the state and the nation, and a national, international security has a huge function in terms of producing the oil and gas, and particularly airplane fuel, for much of the world. So it's kind of a very important spot on the planet, and it houses about 6 million people. So what are the big problems that we face? Well, we have massive amounts of shoreline erosion. You can see on the shoreline of Texas, anything that's not green is eroding. And you can see that the only places that are green are where we have a large jetty system. Everywhere else is receding on the ocean front, as well as on all the bays. And why is that? Well, we have sea level rise as well as subsidence that's mainly caused by oil, gas, and water extraction. A lot of those operations have stopped along the coast, but it'll be decades before that full subsidence is realized. And you can see some of the predicted and historical trends. We definitely have an increasing relative sea level rise problem. We also have a loss of sediment inputs. Typically, the sediment along the coast of Texas came through the river systems. Pretty much all of those river systems are now dammed with reservoirs for water supply and or flooding. And so we've lost a lot of those inputs, and we're also losing a lot of material through littoral transport and the maintenance and operation of our ship channels, which we have 5 major ports in Texas. 3 of them are in the top 10 ports within the United States. All right, so this is the other side of the coin that we face. We have surge issues. We're very low on the coast here. So if you see the 500-year annual exceedance probability, still water level, this is pretty much purely from surge, and it encompasses much of the coastal zone, and it's going to continue to get worse. As sea level rise occurs, we're going to have bigger problems going forward. We also receive ridiculous rainfall. A few years ago, back in 2017, we had Hurricane Harvey come through and drop over here in Nederland. Can you see my mouse?
Yes.
Okay, so over here in Nederland, we received 60 inches over 5 days. Where I live, just south of Houston, we received 48 inches. So we see ridiculous rainfall patterns. Basically, the Gulf of Mexico pumps water over the area and it just drops in buckets. And you can see what all the rivers did. It doesn't really show well because they cut out anything that was less than a foot, but approximately 70% of Houston had over 6 inches of water or more on it during the 5 days of Hurricane Harvey. All right, the history. We've also had our share of major events. The 1900 hurricane is still the most deadly natural disaster in American history, anywhere from 6,000 to 12,000. That's how bad it was. They don't even have a good account of how many people died. And it basically wiped out the fastest growing city in America at the time, which was Galveston. We could see that about half the city was completely flattened, which was pretty remarkable at the time. There's some really great stories about how this occurred and why people didn't leave. It's a book and a movie called Isaac Storm. I recommend everybody go watch that. It's absolutely phenomenal when we make assumptions in science and then we apply them as public policy and people listen to us, and it goes horribly wrong. So this storm happened and it completely wiped out Galveston, which at the time was the fastest growing city. It was becoming a banking center of the West. It was actually primed to be a larger banking center than New York within the decade, and it got destroyed. The port moved up to Houston, and so it starved the economic viability of the area ever since. So what actually happened? You can see some of the damage here. Basically, the first 20 blocks or so got pushed across the island back to the masonry and stone structures, and that's where it piled up. It was roughly 3 stories tall of debris. You can see on this picture here the various high water marks. This is Hurricane Ike in 2008, the 2015 storm, and then the 1900 storm, which was called the Great Storm. And you can see the various water levels. So we have these major events approximately every 20 years, and we see a significant hurricane approximately every 10 years. So what did the local city do? So the local interests decided that they were going to solve the problem. So their solution was to build a seawall along the coast that was 17 feet tall. And you can see it in construction here, an absolutely monumental event. And by the 60s, it had been extended to 10 miles long. But that's not where they stopped. The thing that you'll see here is they completed the seawall. You still see horse and buggies on the beach. This is back in the probably about 30s time frame. This picture was actually it was earlier than that. It would have been 20s. So this is the far end of the seawall. And what they were getting ready to do was backfill. So much of the area behind the seawall was backfilled. And here's a schematic of what they built. So a giant gravity wall. And then they came back in behind it and they pumped material up to 17.5 feet high on the ocean side, right behind the seawall, and then sloped it across the island, which is about a mile wide, down to approximately 6 feet above sea level. And this all happened in stages, but primarily starting in the early 1900s. But they ended up moving a tremendous amount of material to rebuild the entire island. That being said, that's called grade raising. And you can see some of these massive stone structures, they actually filled up the whole bottom story. So the bottom story is now basically buried. They couldn't raise it. Some of these structures are just too big and too heavy. They couldn't jack them up, so they just basically filled in the first story. Very similar to what Venice would do. So a pretty amazing process. The local homes of the people that live there, they raised their homes basically on their own. They basically put together money, took out loans, and every home except for a handful were actually raised, and then they filled in under them, as well as all the utilities. And yes, they had a lot of utilities back then. All right, so what about the studies? What has been done to study this problem? Well, you can see that in the 1900s, they studied the area very, very extensively, came up with a great solution, but that didn't really solve all of the flooding problems, particularly from the coastal resiliency perspective. So the Corps of Engineers stepped up in the late 60s and through the 70s. They built and studied Galveston Bay, trying to determine the best way of protecting the system. And you can see here a scale model in Mississippi, Vicksburg, Mississippi, where they studied how they could potentially accomplish a reduction in storm surge into the bay, thus protecting the petroleum complexes along the edge of the bay, as well as potentially the city of Galveston. And this was a pretty extensive report. It actually was in 2 volumes. It was a pretty massive effort because it went over a decade. So what came out of this report, you can see they came up with 2 gate barrier systems. So one was called Alpha and one was called Gamma. And these were selected for completely different reasons. This one is basically sealing off the ocean. And so it's relatively small in length, only about 8,000 feet wide. And then you have this location, which is basically an area called Mid-Bay in Galveston. And it was selected because it wasn't that long of a distance. This is still close to about 30 miles in length, but the water was very, very shallow. It was about 1.5 meters deep. This was the Alpha plan from many years ago. And this is the plan that I showed that was right at the entrance to the ocean, the Gulf of America. And you can see their approach back then was to build an impermeable dike, a Tainer gate system on both sides, and then have an open navigation channel because no mega system had been built at this time that could handle about a 800-foot wide opening. So none of the Dutch systems were that large. And we have to deal with up to 24-foot high surges. So it's a tremendous force you'd have to overcome during the worst of the worst hurricanes. So back in that time, they decided to just leave it open. But even with that significant opening in place, the rest of the system would hold back a significant amount of the surge. And then here's the Gamma plan, which is at the Mid-Bay area. And you can see this approach was a series of Tainer gates, and then once again, a navigational opening that would not close. Now, the more recent studies, the Corps of Engineers kicked off this study. It's called the Coastal Texas Study in 2015. And it took 5 years to complete. And it includes all these features that are shown here. You'd have some potential basically seawall extensions, relocations, jacking up the structures here on the west side of the bay, a large dune system and beach system, environmental restoration projects, revetments, breakwaters, beach and dune restoration, and then a ring barrier around Galveston. But the highlight of this system would be the Alpha plan from 1979. And that was selected after a lot of back and forth and a lot of concepts that were thrown out. And it's the crown jewel of this overall system. Initially, the cost in 2021 was between 5 and 10 billion. That has since risen to around 15 billion to build a gate system. This effort will require about 72 miles of beach and dune restoration, including this section down here. An absolute massive quantity of material. It's going to be somewhere in the 50 million cubic yards of material. And then a lot of restoration projects, oyster reefs, breakwaters, restoration of islands. Just a huge project that goes from one end of Texas to the other, which is about 400 miles in length along the coast. All right, so this is Plan A, which is lined up with the Alpha Plan from 1979. You got a ring barrier around Galveston proper, the main urban area in Galveston, and then a series of beach and dune projects along the beach tying into High Island. That's since been dropped, and they just extended it to a new restoration project being done with local and federal funds. So why would this function? Well, the thing you can tell from this image down here is this whole system in place is basically drawing a line in the sand and keeping the surge out. That being said, the surge will flank either side, but it'll keep much of the water out of Galveston Bay and would allow for a significantly reduced impact from coastal surge. We looked at a lot of different alternatives. Here's alternative B with a different alignment where we step back away from the coast and put a system with a gate right here. That was ultimately not selected, but we looked at a lot of different alternatives, and I believe we ended up with 5 alternatives ultimately that we carried on, but we'll skip over those for the sake of time. So the key feature besides the gates are the beaches. The beaches are not going to be high enough to prevent surge and overtopping from anything above a 4 or 5 category hurricane. But the thing to note here is a significantly improved coastal dune system. It can withstand a couple hurricanes a year, as long as they're not a significant mega hurricane, and still survive or provide the necessary protection for the homes and communities behind them. And it only has a crest elevation of 14 feet as designed. That being said, once we add a significantly larger beach face, we will have a lot of aeolian transport, which will allow us to have the dunes grow naturally through time and eventually get to a proper elevation that will stop hurricanes that are larger with larger surges from overtopping the system. So here's the crown jewel of the project, or the study, I should say. Now, this is just the design that's in the report, and this system is based on other systems around the world that have functioned relatively well and have a long history of cost and maintenance costs. And so these were selected based on reliability as well as the ability to put together a cost estimate that's of high confidence. Ultimately, what we have here is very similar to the Alpha Plan from '79, but instead of having a closed off initial dike here, we have a series of box culverts, which are called environmental gates in this case, to allow flow in the shallow water, because we know a lot more these days about the various flora and fauna that float through here or swim through here. And these shallower edges along the inlets are tremendously productive and useful for spawning species. And then we have a series of lift gates, a handful of islands with large sector gates that would close off some smaller boat gates here and here, and then a series of additional lift gates. And if you're looking at the area, if you know the area at all, you have Bolivar Peninsula, and then this would intersect over to Galveston Island, and this is the main urban core of Galveston Island. This gives you an idea of what the system would look like in scale to some of the larger vessels that come through and would transverse this area, and you can get a feel for what this looks like. And this system is based on a combination of Rotterdam and St. Petersburg. That's what we use to cost it. And so we're fairly certain on what it ultimately will cost. That being said, this one study is part of a systems of systems approach that the Corps of Engineers has taken on. And you can see the things that are circled in green are the coastal Texas items. And then you have a whole bunch of other activities going on that are complementary. So I mentioned the beach system that was being built with local and federal funds, and that's here that connects into the system that the Corps of Engineers is going to build as a coastal Texas study. But then we have a series of other systems that are in existence or proposed to be constructed. These are basically levee systems to protect highly urbanized petroleum complexes and or communities. And you see these multiple systems in place, as well as ecosystem restoration areas to basically restore some dying marshes to provide that protection from overwash and dampening of storm surge. So the Corps of Engineers is not the only one playing in this coastal restoration world. The state of Texas, through the Texas General Land Office, has been working on a coastal resiliency master plan and putting significant money and skin in the game. And they're on their third phase right now. And their current estimate to complete this plan is 1.9 billion. So any of the areas the Corps didn't look at and did not include for ultimate construction in their study, these are included in this this resiliency master plan. And it's a massive activity. But that's not the only studies that are going on. One of the projects that spurred the coastal Texas study to move forward was this concept called the Ike Dike Coastal Spine Alignment. And this was done by Texas A&M, and it's basically holding the line. So their proposal is to basically build a system out on the frontal beach and dune system with a gate very similar to the location we ultimately decided on the coastal Texas study. And so this would keep the surge out of the greater Galveston Bay area. And it would require a gate down here at San Luis Pass and then a gate here at Bolivar Roads. But there's more studies. There's lots of people that are interested in this. So this is a group called the Speed Center, and they have this proposed plan called the Galveston Park Plan. And so this is mainly backed by Rice University. And so what they're proposing is a series of inland islands, which on the next plan I show, you'll see that a lot of these already exist, and they're dredge material maintenance areas for the Corps of Engineers navigation project for the Houston Ship Channel that runs all the way up into the center part of Houston. And this is a massively important waterway. It's the most commerced waterway in the country. And so this system was their approach to basically protect the more urban areas of Houston. And then here is the maintenance and disposal plan for the Corps of Engineers and the Port of Houston's future disposal activities going forward for the next, I think it's 10 years. But you can see much of the Bay Park plan is included here. It's already going to be constructed, and this island is actually being constructed right now. If you look on Google Earth, you can see it being built as we speak. Some of the issues we have in the bay is there was historical mining of oyster shells. So whenever you go to build anything in this bay, you never know what you're going to get. You could have 100 foot of nothing but pudding for a foundation. So it makes it highly problematic. All right, the science. When we're looking at large scale coastal resiliency activities and studies and potentially billions of dollars being put in, you really need to build that on a solid scientific foundation. And so one of the things the state of Texas took on was to build a sediment management plan that is all encompassing. Unlike most coastal sediment plans that the Corps of Engineers does, or states or municipalities, they rarely ever look at the full river systems. That's not the case in this one. They're taking 5 years to develop this plan. It's still not done. It was supposed to be done last year, but it's probably going to be another year and a half. But they're trying to figure out where are all the sources of sediment that historically used to make it to the coast. Why are they not getting to the coast? where our losses come from in terms of littoral transport. And then they're also looking at locations for material that can be beneficially reused and or offshore nourishment resources. And as part of that, this is what they're doing to identify these offshore resources. And so they've completed the upper coast, they've completed a survey of the middle coast, and they've determined just in the upper coast, you have something like 50 million cubic yards of sediment that's within the current protocols of dredging contractors that they can get relatively reasonably priced. And as we move down the coast, we're going to find lots more potentially. And so this is going on still to this day. When I put the slide together about a year ago, they were $5 million into this effort. They're probably closer to 7 at this point. It'll probably end up being close to 10 to identify all the material resources that are offshore and in offshore Texas within both state waters and federal waters. And as part of this overall sediment management plan, they've developed a sediment budget analysis. The Coastal Texas study kicked this off and completed the first statewide sediment budget, and they're taking it to another level using various different numerical modeling programs. I believe this one is Telemac that they're using. And so it's looking at pure sand sediment transport, ignoring clays and fines. And so this work is complete and it's going to be incorporated. So once you know where your sediment is, you also need to know what your sediment is in terms of what's the quality of the sediment, what's the grain size, what is native. And so I helped draft up this approach for the state of Texas to conduct, and we're going to have the most robust data set. Actually, we have this completed already. We have the most robust data set of native sediment sampling. And why do I say that? Because unlike most places where they sample just the beach berm, and they might sample a handful of places and composite them, we're sampling the dune, mid-berm, swash zone, first bar, trough, second bar, and then we're compositing those. But first we're running them individually, then we're compositing them numerically, and then we're compositing them in each basically region or beach system or barrier island system. So we have a good understanding of what each barrier island is made out of, at least in the active zone. So the state has been closely involved. They are the local sponsor on the Coastal Texas study, but they're also doing a lot of large-scale regional planning studies, and all these are being nested together as much as possible and leveraging activities that have been done in the past. And so we're studying not just the coastal zone, but we're also looking at pluvial and fluvial flooding problems, developing models throughout the entire state. We've actually completed HEC-RAS models for the entirety of Texas. And so that's something that's a big deal. When I moved to Texas in 2016, only the major cities had HEC-RAS models, which was about 5% of the state. Now we have full coverage. And so we can leverage that with our offshore coastal models. And so what we're ultimately trying to get to is a point where we have a solid approach, a point of attack to deliver resiliency. So whether the money's coming from the federal or state government, right now, the state government is pondering an infusion of funds into the flood infrastructure plan for the state of Texas, which is a $5 billion one-time infusion to match the federal dollars, which should be split at a 35-65. So they should get basically another $10 billion from the federal government to match this year's legislative sessions money that they're going to put into riverine and coastal projects. All right, so now I want to get into a little bit more detail on the Coastal Texas study. That's what a lot of this should be focused on, but I had to run you through the historical context. But what I wanted to show here is this is Galveston Bay, and this is West Galveston Bay. And the thing to note here is the various colors. This is a survey from 1962. This was the last survey done with a lead line. And the thing I want to show is you can see the historical mining areas I mentioned before in this dark blue. Those are areas where if you drop this, I think it's a 5-pound weight, how far it would sink. Some of these blue areas are 120 feet deep. So and they were filled up to basically 10 to 12 feet deep, but it was just pure fluff. So if we're thinking about putting a gate here in Bolivar Roads, right where this red line is, we have an 8,000-foot wide opening. We have a depth of approximately 60 feet for the navigation channel. And we need to have a navigation opening of somewhere between 800 and 2,000 feet. And we probably need to have a navigational depth ultimately of 70 feet. That being said, we have a lot of environmental factors we need to keep in line with. We've been in negotiations with a lot of the environmental agencies, and they will allow us to reduce the total tidal prism exchange by up to 40%. Ultimately, what would be ideal is to have no net change in exchange. And why do I say that? It's probably going to be about a $4 billion mitigation effort to offset the environmental damage from reducing the tidal exchange in the bay. And so we also need to approach the navigation gates, the tidal exchange gates, and intertidal environmental gates completely differently. So here is a cross section right across Bolivar Roads, right where the gates would go. And these vertical bars that are black are the foundations and the concrete substructure that would be in place if we built the current Coastal Texas study plan. So that'll give you a good idea of what we are talking about in terms of reduction and tidal exchange. So looking at this, we're going to be breaking up the flow, and we have a very stratified flow here. We have much more salty water at depth versus the surface water, which is much more fresh. Moving beyond that, when we look at the geology of the area, what we're proposing to do occurs right in the Paleo Valley of the former Trinity River from 17,000 years ago. And so you can see this cross section, it's actually shown right here. But that's also a very similar cross section of what we would have right at Bolivar Roads. So this is a good representation of what we would expect. And what you will notice here is we don't hit hard clays, which is this red line. We're proposing to put the gate system till right about here, which is about 160 feet to 175 feet deep. So we're going to be building on a floating foundation with whatever vertical structures we build, and then building a gate system that's got to hold back 8 to 10 meters of surge potentially, and building that on footing. That's going to be a huge design challenge, but it's something we definitely can do. It just adds cost and complexity. There we go. All right. So all these different factors, they really do end up driving the design of the gate. And so you also need to think about what's the criteria for closure, how often are you going to close it, what are your operational problems that are going to arise in terms of maintenance. So the tidal prism reduction is a huge problem. Back when we completed the report in 2021, the estimate was about $1 billion in mitigation cost. That has risen to several $billion. We also have to deal with these islands, and these islands are going to be absolutely massive. We're talking millions of cubic yards of fill. And then the vertical structures that make up this entire system will impact the flow and cause some potentially detrimental mixing. We have the geotechnical conditions of the Paleo Valley. And we need to think about how to deal with that, whether we're going to build on a pile foundation or a spread foundation, or are we going to consolidate the sediment like the Dutch have done on some of their mega structures. And then we ultimately need to think how these things tie back to the operation of this system in a hurricane. And so when we're thinking about a hurricane passing, I have three examples shown here. And the takeaway is, if you have a hurricane coming in on this beeline right here, you would have much of the surge hit the northeast quadrant, and we wouldn't see much of an impact, right? This is the current system that we have in place. We had Hurricane Ike come through in 08, and it went right through here. And this is basically Hurricane Ike moved 30 miles basically to the northeast. With the current existing condition, you would see no real detrimental issues in the bay. Now, if you go ahead and run that same storm with a closed gate here, you end up having a lot of back bay flooding because the water can't go out the gate because the gate's closed. And so you have what's called inducements, which is going to be lots and lots of lawsuits, which will tie up the courts and cost whoever is the owner of this system billions of dollars of losses and settlements. That being said, if you go ahead and build the entire project and are able to open the gates as the hurricane is passing, you end up with no real impacts in the system. Because you're able to, once the storm gets on land and the clocking winds, it will just push it right back, push the surge right back out of the bay. And you'd never have a major surge enter the bay. So the way the Corps of Engineers is approaching all these things, as well as the General Land Office, the state, is we're looking at a multiple lines of defense strategy. We have a lot of things already built that are historical structures, flood walls, gates, levees, but we need to build additional features, build a larger dune and beach system, potentially elevate some buildings or do relocations, and then potentially additional renourishment and or marsh creation and oyster reef creation projects. And so that's the approach that we're taking. We're not putting all our eggs in any one basket, because we have issues not just from coastal surge, but we also have major rainfall events that can cause equally as much or more damage than a hurricane surge. And so the way we're attacking this is, first of all, through science and technology, as I've displayed in this presentation. But we also are trying to align all the projects so that they're complementary and not detrimental to one another. A lot of the projects are in several of the plans, so whoever gets money first gets to build it first, and the other team that was trying to build their thing just takes that off the board and moves that money to other priorities. Sediment management is a huge activity that we're dealing with in our area. It's something that we are experiencing a loss of. We're in a massive sediment deficit, and sources are scarce. That being said, we do know there's a lot now, a lot of sediment sources, but they're not super convenient. They're not within the 10-mile pump distance for a large cutter suction dredge. And so that does pose increased costs to the system. Some of the things we're looking at are bypassing and backpassing systems, additional coastal structures, and sediment traps, and then using that material beneficially in the system. And so one of the things that we've been striving for is to ensure that anything we build is built on solid empirical sound science, not just trusting the models. We need demonstration sites, we need a proof of concept before we invest hundreds of millions or billions of dollars in any one approach. And so how are we going to accomplish this effort? First of all, we're going to use historically well proven systems like terminal groins as growing fields, breakwaters, anything that has been used in the past, and we find the right function. Like this is Follett's Island right at San Luis Pass. We're going to put 1 million cubic yards roughly in this 10-mile section. It'll probably end up being closer to 2 million, all said and done. But if we do that, we're going to have tremendous amounts of sediment escaping the island into the navigation channel. We need to add other features to trap that sediment and backpass it. One of the big issues we have is pretty much all our sediment sources are not nice, fine, clean sand. They're mixed with muds, clay lenses, and silts. And so we have to develop technologies that can at scale remove undesirable material from the material we put on the beach. And then utilize those fines in areas like marsh replacement areas. So a lot of the areas that we have are subsiding tremendously, a centimeter roughly every 5 years. And so we need to put that sediment back on top of some of these marshes, particularly the fine material that will flatten out and cover areas. And so we are testing different technologies. We're doing this sand mud separator project or proof of concept. It's something that we need to continue to push and develop and bring up to scale to do mega projects. But before I move on and open it up for questions, I wanted to show you guys that there are tons of gate designs out there that we've looked at that have been used and investigated around the world. So you have the Maasland barrier in Rotterdam. You have the Eastern Scheldt barrier also in the Netherlands. And then at our location, you have lots of other concepts. So this was a design put together by the New Orleans district. And so this is a series of floating sector gates and then a bunch of barge gates that would be sunk into place the one time every decade that we need to close the system off. You have the MOSE system, which is basically a flap gate hinged. And the Japanese, as Giovanni alluded to, are also designing systems that are very similar to the MOSE that are self-closing as the tsunami approaches. We've also had other university professors and their students develop concepts. So this is a piston gate system that we brought up to about a 10% design, which would work at a significantly lower cost than the Coastal Texas Study Plan. It's just not as reliable and proven. That being said, we're looking at surge barriers all around the world, investigating them, learning what their pitfalls are, their maintenance problems, so that we can identify the right system. I'm not going to go through all of these. I'm going to skip through most of them so we can go to questions. And I'll show you guys my last slide that I want to share. So this is a map or a plot of all the different mega coastal gate systems that are in place. You have Seabrook, which is in New Orleans. You got some systems that are in the Netherlands. You got the ones in Britain, one in Russia. You got Venetian and the Eastern Scheldt. And basically what this is mean flow tide versus opening size, and you plot them. And the thing that I found when I plotted Galveston, it fell right on top of Venice. It's almost the same sort of system. So that's why we've reached out to the Venetians to learn from their experience, because our system, the size of our bay, the flow through our system, and the exchange daily and the tide height is almost identical. So with that, I'll open it up for questions.
Thanks so much, Coraggio. On that last point, though, the kind of comparison with Venice, I mean, you have huge river systems coming in behind, whereas in Venice, those have been diverted. Does that make for a significant need for pumping on your end that wouldn't have been needed in the Venice example?
So not really, because of the subsidence we've experienced over the past, I guess it was 100 years, we've seen about 4 feet of subsidence across all of Galveston Bay. So the amount of infill has not kept up with the rate of subsidence. So back in the 1880s, there's images taken of cows fording across Galveston Bay right here. That's now 6 feet deep due to a combination of excavation for mining of oyster shells and subsidence.
So you're saying you have storage capacity, you would have storage capacity in the bay?
Yes.
Got it. So you have a question from Phil Orton about the speed plan. That was sort of complete, like all the other plans seem to have a very similar concept of building up along the coast and some kind of a barrier, but this is a very different concept. Can you talk any more about why it's so different?
Basically, the approach of the speed plan is to do it quickly and at a lower cost. The costs, those shouldn't be too hard to nail down, but it's going to be billions of dollars regardless. And much of it has been built. So if I show you guys a speed plan, I click over here to what has been built or is proposed to be built, we would basically build the speed plan over the next 30 years without even needing to do anything other than just maintain the channels and the ship berths. So the speed plan is a complementary plan, in my opinion, another line of defense from keeping the water out of the system. So it is much, it's basically falling back, but I think it's a complementary line of defense. It's not going to solve all the problems, particularly when you look at Galveston. It's going to get absolutely destroyed by any major hurricane. So, to really solve the larger issue more holistically, you would need to have a first line of defense.
I see. But this concept is basically you allow the surge to come into Galveston Bay, but you keep it from going sort of to the southwest. You kind of make sure it goes to the northeast mostly.
Yeah, this area is relatively, it's got a much lower population. It's not urban and dense like the west side of Galveston Bay and Houston, which is up here.
Right. Looking at the questions here. So Lewis is asking a question that actually was on my mind as well. I mean, these are massive, technologically complex projects you're talking about. At some point, is moving Galveston, is that sort of off the table 100%, or is there some scenario here where it's more cost effective to have some managed retreat as opposed to the sort of protection approach?
Well, the answer is probably not. There's 50,000 people that live just beside this ring barrier. And a lot of these areas are historical, low to moderate income communities. They got pockets of areas that are very historically active. They're not going to, take being kicked out of their homes very well. And then if you look at this ring barrier system that's being proposed, and I didn't even go into that, but this is a several $billion project, which will basically build a 10-foot high or 10 to 12-foot high barrier on the backside of the island, connecting to the existing seawall, which is at 17 feet. And so that would solve a lot of the problem. But if you get a Cat 4 or 5 surge, it will overtop the backside. You'd have to go to 15 feet or so. But then you would cut off people's ability to enjoy the rest of the decade, right? We're only seeing significant hurricanes once a decade. So in that case, is the juice versus the squeeze, right? If we get a significant hurricane once a decade and a bunch of the homes flood, is it better just to raise the homes that flood in the future? And a lot of these homes are made out of wood because they're historic and built right after the last great hurricane in 1900. And so they can be raised, and they have been raised. A lot of them are already on elevated foundations. You just elevate them a little bit more. I don't think we'd grade raise the entire island again, but this whole area that's hashed in yellow has been grade raised back in the 1900s to like 1920.
So in some sense, this ring barrier is similar to what Giovanni was talking about, the super levee concept, right? But
Yes.
it strikes me that it has, as you just said, if you don't build it high enough or big enough, it actually has built into it a really, really challenging vulnerability. Or if it's overtopped, you're now, and on top of it, as you started out by saying how much rainfall you guys get, if it's overtopped and, you're getting 10, 20, 30 inches of rain, that's a pretty significant risk, I'm guessing.
Yeah, they currently have designs for giant pump stations, and they're building some of them already without even that system in place, just because they have such a local urban flooding problem.
Yeah. So Philip is asking a question about closing the inlet barrier. Is it based on, how frequently is it going to be closed? Is it based on forecasts or, and how do you deal with sea level rise and sort of thinking about all that?
Well, we haven't gotten there yet. It's all conceptual right now, but it'll really come down to how the barrier is ultimately designed and built. But the current concept is we would close it about 24 hours in advance of landfall. We have to give the U.S. Coast Guard a minimum of 24 hours to clear basically the port out. So all the big ships have to leave. They have to go out to sea, and that requires 24 hours to get them all out. And then we would close it 24 hours in advance of landfall. It would be purely based on the forecast. And as you guys are probably well aware, it's very hard to nail down exactly where a hurricane in the Gulf is going to hit. And 20 miles either way of the ship channel would have a completely different impact. So if it hits a little bit to the east of the ship channel, then we have not any real significant problems. We would just keep the system open and let it run. But if you're dealing with how that thing is going to possibly shift, you're going to have to make hard decisions, and we don't have that nailed down yet. That would be a terrifying job to have, to make that call, to close or not to close when something's bearing down on you.
Yeah. And so all of these projects, I mean, you talked about what the state of Texas is doing, what the Corps is doing, what some of the universities have proposed. Unless I missed it, I didn't understand like who would be the mastermind behind all of I think what you said is that whoever gets the money first is going to do that flavor of the plan. But what's sort of the organizational structure here, and like who would be responsible?
So for the Coastal Texas study, they've actually stood up a new entity called the Gulf Coast Protection District, and they're going to be ultimately in charge of the hard structures that are constructed. The GLO will be in charge of the marsh creation areas and the softer, more bugs and bunnies thing. But the flood walls, the gate systems, that's going to be handled by this other entity in terms of operations going forward. They're staffing up right now. It'll be some time before we ever get anything in the ground that they have to maintain. So there are a lot of components going on, but we all talk together. So the academics, the Corps, the state, the Gulf Coast Protection District, the local communities, we meet on a regular basis at conferences, at various presentations and meetings that occur. So we're all pretty much in it together. We all know each other, and we're trying to work for the common good to make it happen.
That sounds mind-boggling, the level of complexity involved.
Yeah, that's why we need a holistic approach. We can't just ignore what everybody else is doing, because we're all playing in the same sandbox, literally.
I wonder, in the 5 minutes or so that we have left, if Giovanni, if you're still here, if you want to come back on and we can sort of maybe talk generally, answer a few other questions. I don't know, Coraggio, if you want to stop screen sharing for a moment, we can. Although I don't see Giovanni here anymore. He may have.
I see him now.
Here.
Oh, there he is. Okay, there you are. So, what's interesting, I guess one sort of comment I'll put out there before we get into some specifics that are remaining from Giovanni's presentation is that it does seem all of these projects seem to, it's sort of false that there's like a gray or green approach. I mean, all of these projects seem to be taking, there's some really significant engineering, sort of hard gray infrastructure built in. but it seems like in both Venice and Galveston Bay, the sort of natural system piece of it is part of that. Is that sort of the state of the art that you'd say right now, is that they're in this kind of coastal protection? It's, although I guess Coraggio, you talked about that a little bit less than Giovanni did. But you did mention some of the islands and some of the, some of the parks and some of the other spaces. But are all of these projects sort of intimately marrying to the sort of ecosystem restoration, nature-based solutions approach with the gray approach?
Okay, is that question for me or for Giovanni? But I would say in the Texas case, yes, anytime we build something massive that could disrupt the system, we're typically at a minimum including green infrastructure to protect, let's say, the toe of the structure, or back surge, or to dampen the wave impacts from episodic events. So we're using nature to protect the critical infrastructure that we're putting in the ground.
Yeah.
If I may add, it is an early integration. So we need to take into account with a holistic view all the potential of the system. And of course, we have to play with nature. It is important to accept this concept of co-evolution. So nature is impacting on the social setting, and the social setting is modifying the natural evolution. Instead, if you put nature on top as a deity, ideological approach, then you go into trouble, because nature is not taking care of us. Of course, we need nature, but not in an ideological fashion. We need to know the functioning of the lagoon and adapt and take advantage of the natural processes. Usually, when there is a proper co-evolution, we allow space and time to nature to accommodate to our infrastructure. As I've shown, the biodiversity is increased. But this is not sometimes acceptable. I want to bring the example of Cardiff Bay. They were considering to install hydro plant using the tide, with a certain number of ponds that could be filled in and out by the tide. And a friend of mine did the environmental assessment, and the project was stopped because this intervention would modify the bare soil of the ocean there. Increasing the biodiversity was felt as a source of manipulation of the natural setting. This was 15 years ago. So sometimes the regulations are not rational, my opinion. Of course, there is an emotional and personal and dignity attitude. If I live in that landscape and I feel myself as a part of that landscape, and you come for your own purpose, because I don't care, because I live in a barge that is floating, and you want to change it, it can be an issue. So we need a dialogue to take all the value of the people, to listen to the people, and allow them time and space and resources to adapt. So this is the very secret of adaptation. Listening to people and try to integrate them into the process, providing them a certain amount of rational. Otherwise, they will give more value to the irrational and to the sentiment that are very difficult to agree with.
Yeah, and I would sort of argue that both things you mentioned, just listening to the people and working with the natural systems, although we kind of think of them as the green approach as opposed to the gray approach, they're really just good engineering, right? I mean, how good is your engineering if you're not considering the natural systems, and if you're not seriously considering the needs of the community that you're trying to serve? So it's interesting how we've sort of bifurcated it into these two different approaches, but really the integration is I think just good engineering.
there is a persistence law. We tend to persist because we are lazy. Also, nature is lazy. The species tend to make an environment that is easier to stay with less stress and less changes. So we are along the same line, we and nature. The only problem is not to do things very rapidly and without allowing the others, the nature, to have its own space for regeneration and recovery.
Yeah. Well, we'll have to leave it there. Unfortunately, thanks to both of you. There's a really so much information provided in these presentations, and I apologize to the folks who added questions that we didn't get a chance to address, but these presentations will be posted, and if anyone has persistent questions and you want to email them to me, I can send them out to Coraggio and Giovanni separately. But thanks to the both of you. These were really excellent presentations, lots of material, lots of stuff to think about, and keep doing this important work.
All right, thanks a lot for having us.
Thanks.
Thank you.
Bye-bye.